Hey everyone, in this video we will investigate the very fundamental concept of word vector in the context of Spacy library. So a word vector is basically a dense representation of a word, and word vectors are produced by algorithms that make use of the fact that similar words appear in similar context. To capture the meaning of a word vector algorithm collects information about the surrounding words that the target word appears with. So this paradigm of capturing semantics for words by their surrounding words is called distributional semantics. So semantically similar words have similar word vectors, and hence word vectors are great for semantic similarity applications such as calculating the similarity between words, phrases, sentences, and documents. Now, there are quite a few popular ways to produce word vectors. Let's look at the most popularly used one, which are word2vec, globe vectors, and fast text. These word2vec is the name of the statistical algorithm that was created by Google to produce word vectors. Globe vectors are trained in another way and were invented by Stanford NLP group. This method depends on singular value decomposition, which is used on the word co-occurrence matrix. And fast text is another one very popular, and this was created by Facebook Research. So fast text is similar to word2vec but offers more functionality, I mean. So word2vec predicts words based on their surrounding context, while fast text predicts subwords, that is character engrams. For example, the word chair generates some sub words, for example ch, ha, ai, ir, that is taking various parts of the single word. So fast text produces a vector for each of these subwords, including misspelled words, numbers, partial words, and single characters. It's very robust when it comes to misspelled word and rare words. And fast text also can compute a vector for the tokens that are not proper lexicon words. And if you want to install or use fast text with semantic with Spacy, you can download the model from here. This is their official docs, fasttext.cc, and you just need to run these command lines from your bash script, or you can also do it with Python. Now, these were some of the external or third-party word2vec vectors, very popular. There are even a few more. For example, another one named something like Google News. That's 1.5 GB of model file, and that's also very popular. I did not discuss that specifically here. I will cover that in a separate video altogether. And now coming to Spacy, we have in Spacy 3 of them. So I'm looking at the Spacy's documentation. I have one N-core web SM, which is the smallest one. SM means small. It's a 12 MB file, and these have 0 keys, 0 unique vectors, and 0 dimension. Then I have MD, which is 31 MB file. It has 685,000 keys and 20,000 unique vectors with 300 dimension. And finally, I have this vector model N-core web LG, which is for large. This is very useful one, because this large one, although the file size is more, that is 382 MB, but the vectors included in this is very effective in producing useful and significant result. So it has got 685,000 keys, 343,000 unique vectors, and 300 dimension. Now, what is out of vocabulary in Spacy? So only the words in the model's vocabulary has vectors, and words that are not in the vocabulary are called OOV, or out of vocabulary words. And we can check that by using two methods from Spacy. They are called isOOV. That will check whether a particular vector is OOV, and also we can do a token.hasVector method to check if it has a real vector at all. So basically, if has vector returns true, that means That means a token is in the model's vocabulary and has a word vector associated with it. So let's do a random text. In this random text, you went there AFS, KFSD. So this part doesn't have any meaning. It's not in the vocabulary. It should not be in the vocabulary. And now I'm using is OOV and token.has vector. Let's run this cell to see the output. Yeah, as expected, I'm getting for each of the token is OOV and has vector as false, true, false, true. So basically, this is looping through each of these words. So for example, the first word, that is OOV, should be false because that's part of the vocabulary, and I'm getting false, and has vector is returning true. Similarly for went, I got false, true, then true, false, and there this AFS, KFSD, there I am getting is OOV is true, and has vector returning false. And if you are wondering then why I'm getting another element as the last one as false true, I mean, why there are 1, 2, 3, 4, 5 tokens when I have 1, 2, 3, 4 words? That's because this last period that you see, this full stop symbol, that is taken as another token as per Spacy's inbuilt vector. And we can check that by running this again, this code, but this time simply printing the tokens only. So I'm running the same string and I'm only printing the token, and run this cell, and I get you went there AFS, KFSD, and the last one is that period. So that's how I'm getting 5 different tokens. All right, now the next topic is the similarity method within Spacy. So in Spacy, every container type object has a similarity method that allows you to calculate the sentiment similarity of other container objects by comparing their word vectors. Let's define 2 documents with random text. Yep. And remember again, this NLP that I'm using again and again, this is just creating the object from these MD vectors. So where did I define it? Here, NLP equal to spacy.load ncore web MD. That's where I defined the NLP. So here I just have 2 random text. Now check their similarity across these words, these tokens. So let's print this, print doc 1, 2, 3, that I'm taking slice 1 up to 3. Similarly here, doc 2, 1 to 4. And you do this dot similarity between this doc 1 and doc 2, and let's run this cell. All right, I'm getting 6, 8. That is the similarity is relatively on the higher side. Now quickly check what their official documentation talks about their similarity. So this is their link, and I am in their official documentation, word vectors and semantic similarity. So similarity is determined by comparing word vectors or word embeddings, multi-dimensional meaning representation of a word. Word vectors can be generated using an algorithm like word2vect, and usually looks like this. Okay, now let's go down. I just want to point out few of the limitations of their similarity measurement. What to expect from similarity results is yes, this is important aspect to read about. Computing similarity scores can be helpful in many situations, but it's also important to maintain realistic expectation about what information it can provide. Words can be related to each other in many ways, so a single similarity score will always be a mix of different signals, and vectors trained on different data can produce very different results that may not be useful for your purpose. Yeah, so this is important to remember. Spacy's similarity matrix has its limitations, and also you cannot just depend on a single similarity measure to calculate your similarity. For example, there is no objective definition of similarity whether I like burgers and I like pasta is similar depends on your application. Both talk about food preferences, which makes them very similar, but if you are analyzing mentions of food, those sentences are pretty dissimilar. Yeah. Also, vector averaging. Okay, this is important. The similarity doc and span objects defaults to the average of the token vectors. This means that the vector of fast food is average of the vectors for fast and food, which isn't necessarily representative of the phrase fast food. Also, vector averaging means that the vector of multiple tokens is insensitive to the order of the words. Two documents expressing the same meaning with dissimilar wording will return a lower similarity score than two documents that happen to contain the same words while expressing different meanings. Yeah, so we will explore these limitation of similarity in Spacy with an example. So basically, this kind of result that why we are getting is explained by what we just saw in Spacy's official documentation, that how word vectors are calculated. So basically, each word has a vector representation learned by contextual embedding word to vec, which are trained on the corpora. Now, the word embedding of a full sentence, that is a full sentence containing many words, is simply the average over all different words. So if you now have a lot of words that are semantically similar or lie in the same region semantically, for example, filler words like he, was, this, all these things, then many of those additional vocabulary cancels out, and then you might end up with a similarity as seen in this example. So in any ordinary sentence, there are a lot of meaningless words which are called stop words. You get poor results. So one way you can remove them and create your similarity score again is like this. Let's do it in this cell. Yeah, so now I have those two random search doc and main doc defined again, and what I'm doing in these two lines, that I am removing all those stop. So what I'm doing, joining all these words and just removing for t in search doc if not in t dot stop. So this will return me a boolean. If this boolean, if this is not true, only then I'm adding them with join and then calculating my similarity, that is search doc no stop words and main doc no stop words. Let's run this cell. Yeah, now I'm getting now this is reduced from 0.93 to 0.79, quite a drastic reduction, but still I would say still this similarity score is relatively on the higher side, given these two sentences have very less similarity. So that was enough talk about similarity in spaces, and the next one I'm going to just visualize the distances between words by plotting them with matplotlib. So yeah, distance visualization. So what I'm going to do is I will have two sets of words, one for food and another one for different animals, and let's see how they plot in a two-dimensional space. So first, just going to import all my relevant packages: matplotlib, sklearn decomposition, pca, and numpy as np. And we will see in a second that why I need this pca, principal component analysis part here. I already have my NLP loaded, so let's define my vocabulary. So this is my example vocabulary. So now what I have is dog, puppy, turtle, rabbit. All these are animal names, and then I have burger, pizza, food, cheese, wine, noodles, all these things. And now I am just going to create a words variable. Word dot text for word in vocab. And because this vocab is a document object, I get access to quite a few this kind of methods to get their content. So here word.text will give me the actual text of the this document object. So for example, for the first one I get dog, for the second one I get puppy. Similarly, and I also need to stack the vectors. So VECS equal to vertical stack, and what I do, word dot vectors for word in word dot has vector. Yep. Sorry, this is not what I wanted. Word dot vector for word in vocab if word dot has vector. Yeah, so I'm checking if word has indeed a vector, that is it is part of the corpus of Spacy, part of the model, part of the vocabulary, that is it has some meaning. And then if it has vectors, then I'm vertically stacking them. Otherwise, if it does not have a vector, then I will get error. So this has vector will return me a boolean true false. And now I am going to define a PCA. So now the reason, since the vectors are all 300 dimensional vectors, we saw that, right? We saw in here, that is Ncore WebMD. This is 300 dimensions of vectors, and hence I need to reduce the dimension. And what I'm going to do here, we needed this project projecting into two-dimensional space for visualization purpose. So we made this projection by extracting the two principal components via PCA. CA n components equal to 2. Yeah, that will reduce all the 300 dimension to 2 dimension. And then I also need to apply fit transform, because so I'm going to use fit transform together. And as you know, probably that fit method, which learns model parameters, for example mean and standard deviation for normalization from a training set, and the transform method, which applies this transformation model to unseen data. So here I'm not doing any modeling, so I have just one single piece of data, and I can apply fit transform together for more convenient and efficient calculation. Vex transform will be PCA.fit transform vex. Yeah. Now just my plotting methods. Let's zoom out a little bit. PLT dot I'm going to do fig size equal to, let's keep 20 comma 15. It would be a scatter plot, so I can see all the scattered view of the words in a two-dimensional space. SCATTER vex transformed, and I'm going to take the 2 dimension. So first is my first dimension, then second dimension. And now for word coordinates in zip. Why I'm getting all this red? This is unnecessary syntactical error. Words and what is that? I have vex transformed. Yep, x y equal to coordinate, and then plt dot text xy word size would be equal to 15. Let's run this cell. Awesome. So we can see that in the plot, in the scatter plot around the 2 dimension, I have got all these foods towards this cluster, and the animal, mouse, parrot, turtle, or fish, towards the top right corner. So they are kind of clustered differently. So it's kind of working, the similarity. And now I'm going to check the sentence similarity with Spacy. Now, for calculating sentence similarity in NLP, there are quite a few advanced tools, for example, sentence transformer, etc., which will give better result, obviously. But with Spacy as well, you can do some fundamental similarity checking between sentences. And for that, first let's understand what is semantic similarity. So semantic similarity is a metric that is defined over text, where the distance between two texts is based on their semantics. And a metric in mathematics is basically a distance metric, and we have the most popular two distance metric, which is Euclidean distance here, and another one is a cosine similarity distance. This is how cosine distance is measured. Now, what does the Euclidean distance mean for word vectors? Now, obviously, we can see that how it is calculated mathematically. Xi minus yi, you take whole square, you sum all of them, and then take a root over of the sum. Now, the problem with Euclidean distance is that this distance has no idea of vector orientation. What matters is the vector magnitude, because we are only taking the magnitude of these two vectors. And this is the main drawback of using Euclidean distance for semantic similarity, because the orientation of two vectors in the space is not taken into consideration at all, and which is important for calculating the semantic relation between two words. And hence there is another way for calculating similarity between two words which addresses this problem, and which is our cosine similarity metric. So contrary to Euclidean distance, cosine distance is more concerned with the orientation of the two vectors in the space. The cosine similarity of two vectors is basically the cosine of the angle that's created by these two vectors. And under cosine similarity, the maximum allowed similarity between two sentences or two words is when the score is 1, and that 1 is obtained when the angle between two vectors is 0 degree, meaning the two vectors actually coincide. And on the other hand, the similarity between two vectors is 0 when the angle between them is 90 degrees. So cosine similarity provides us with scalability when the vectors grow in magnitude, because if we grow one of the input vectors, for example, in this case, if any of these vectors is grown infinitely even, the angle between them remains the same. So the cosine similarity score remains the same. And Spacy uses cosine similarity to calculate semantic similarity. Hence, when I call the similarity method of Spacy, we actually make the calculation for cosine similarity metric. Let's do that with a quick code. Here I have three docs defined with NLP. Remember again that I'm always passing the actual raw strings through the NLP, because I need to get the doc object. Otherwise, all these methods, etc., I cannot apply on them directly on the string. So here I have three docs, three sentences. The person wear red t-shirt, this person is walking, the boy wear red t-shirt. So this third line, doc 3 and doc 1, should be, the similarity should be higher. But between doc 1, doc 2, similarity should be lower. Let's see what they produce. Run this cell. Yeah, as expected, doc 1 and doc 3, that is this one, the second one, I got a high similarity, 90.95. But between the others, they are not similar, so I got a low similarity, 0.46, 0.37. Yeah, so this very much makes sense. Now remember, this was the most simplified way to produce result of similarity checking with Spacy, but obviously there are a few text processing that you need to do for any more serious project. So we already showed one which is removing the stop word here. Where did that go? So one second. Yeah, here. So we removed the stop words here with t dot is stop. And further few things you can do is removing all punctuation, also removing pronouns, and only after removing stop words, punctuation, and pronouns, then you can run your similarity measures again with Spacy. And then definitely that will definitely improve your similarity score, and that will be more meaningful in terms of actual similarity between words or sentences. Now, before ending the video, I just want to quickly show the method that you can use to remove your pronouns from any given text. A quick method, and I'm going to use. So again, always you have to get your doc object NLP text, and then I'm going to use a method from Spacy, which is token.lemma underscore, which will give you the pronouns in a token. So here I'm sorry, result, spelling Mr. Gari, SULT. Yeah. So now token for token in, what I'm going to do, doc if token dot lemma, LEMMA underscore is not equal to you have to pass this PRON. And why I use just this particular string, because that's how token.lemma will produce a pronoun if it finds one, and this you will get from the official documentation of Spacy. They have explained all these attributes very well there. It is well defined. Okay, so that's how I'm getting after removing the pronouns, and then just you join the result. Return join with a single space, join. That is all. So this function will remove your pronouns from any given text. So yeah, this kind of basic text preprocessing you can do of removing stop words, punctuation, and pronouns, and then pass that text to your Spacy similarity metric to get much better result. All right, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.